Motors. A motor converts electrical energy to mechanical energy. If a current is passed through a conductor, which is positioned in a magnetic field, a force will be exerted in the conductor. The principle of operation of a DC motor is the reverse of that of a generator. A current being supplied to a coil within a magnetic field so that the coil moves according to Fleming's left-hand rule for motors, where the thumb indicates the direction of motion of the conductor, the first finger the direction of the field, and the second finger the current flow. Construction is similar to that of a DC generator. In most applications, the motor and the mechanical sections of actuators, control valves, pumps, and instruments form integrated units. The power supply required may be 28 volts DC, 26 volts AC, or 115 volts constant frequency AC, applied almost without exception by direct switching and without any special starting equipment. The type of windings commonly used in DC starter motors are typically series wound. Many motors are required to operate only for a short time during a flight. Ratings of between 15 and 90 seconds being common. After operation at the rated load, a cooling period of as long as 20 minutes may be necessary. Continuously rated motors are cooled by their operating medium, air conditioning by ram air or an induced airflow, and fuel supply pumps by fuel. Where motor operating speeds are high, reduction gears are used in the transmission system. If you look in your flight manual, you will probably find out that you should not be operating your flaps up and down repetitively, which can occur during training flights, as there is a real risk of an electrical fire in the flap motor in the wing. Speed and torque characteristics determine the type of motor for a given application. The variation of speed with armature current is determined by the back EMF present due to Lenz's law, which is itself governed by the mechanical load on the motor. The torque characteristic is the relationship between the torque required to drive a load and the armature current. A motor, if you think about it, is essentially a generator. It turns, has poles, and exists in an electrical field. So guess what? It produces current, but in the opposite direction to that which you desire. If, say, 28 volts DC is applied to a motor, and the motor produces a back EMF of 20 volts, the resulting power is determined by the difference, that is 8 volts DC. If the mechanical load on the motor increases, the motor slows down and the back EMF reduces. With less back EMF, armature current increases, applying more torque to the motor. The motor speeds up, and at some point, armature current balances the load. At startup, back EMF is 0, so starting currents are typically very high. This would be, let's say, your electric lawnmower going through long grass, or a drill hitting tough concrete. Back EMF decreases, so more current can flow, burning out your motor. There's a formula for synchronous speed for motors. Synchronous speed equals frequency multiplied by 60 divided by the number of pole pairs. So for example, what is the speed of an asynchronous 4-pole motor fed at a frequency of 400 Hz? 4 poles means 2 pole pairs. So the formula would be 400, the frequency, multiplied by 60 divided by 2, which is 12,000 RPM. Motor reversal. The motor is reversed by changing the phase rotation sequence by switching 2 of the field terminals. Reverse the polarity of either the stator or the rotor.